Today we want to continue our look at line integrals. We're integrating a vector field over a parameterized curve, a parameterized oriented curve. That was a weird collection to put together. An oriented curve, which we'll parameterize. Maybe that's better. And we're going to turn our line integral, integrating the vector field f over the curve c dr into this single variable integral by parameterizing the curve. So here's an example. We've got our vector field is going to be 6xi plus yj. And I've got these two different curves. C1 is the line from the point 2, 0 to 0, 4, and C2 is the parabola from 2, 0 to 0, 4. And I want to calculate the integral of the vector field over both of these curves. So this should be suspicious. I'm asking you to integrate, in one problem, I'm asking you to integrate a vector field over two different curves with the same starting and ending points. So we might speculate on what's going to happen with these two line integrals. Now let's find out. So we need to parameterize the curve C1 and then separately parameterize the curve C2. So let's start with that. So C1 is the line, oops, that's not 4, 0. Earlier today, I was teaching in the alternate universe where we list the coordinates the other way around. So sorry, it's hard to switch sometimes. C1 is the curve from, is the line from 2, 0 to 0, 4. So we've got to write x and y, we got to write parameters, parameter for, we've got to parameterize this line from 2, 0 to 0, 4. So let's start off with describing this line in a familiar way. So this line is, yeah, that's fine. Let's see, we decrease by 4 when x increases by 2. So y is equal to 4 minus, we got a slope of -2, so minus 2x. So this is y as a function of x. But we need to turn that, we need to write x and y as functions of t. All right. So one way to parameterize this curve is to just say x is the parameter. This is not going to work in this case because it's going to go the wrong direction. One way to do this is to say x is the parameter and say if x is t. Do I want to cram this in this space? Or do I want to make a larger point out of this? I think I want to make a larger point out of this. One way to parameterize a curve, if that curve is a function, where one variable is a function of the other, is to just make the independent variable the parameter. If your curve is a function, then one strategy is to start by making the independent variable your parameter. One strategy will be to make the independent variable your parameter. So, let's see. I'll say x, make it stand out. I'll say x is the parameter t, and y is just 4 minus 2 t. Now this is just to get the x and y pairs going. The other thing that we need is the direction and the range, the domain of t. What are we going to plug in? And is this going in the right direction? So we got to figure what values of t are we going for? Well, I just wrote this as x equals t. And so the t values are going to be where the x values are, and the x's go from 0 to 2. So we'll say this for t between 0 and 2. The other thing we'll have to check is that if we have the correct orientation. If I plug in t equals 0, that should be down here at 2, 0. But when I plug in t equals 0 in this case, I get 0, 4. So this is not going in the correct orientation. When t is equal to 2, we'll be at 2, 0. T equals 0 means we're at 0 to 4. And moreover, when t is equal to 2, we'll land at 2, 0. So this is going the wrong direction. Oh, I forgot I wanted to put both points. Oh well. T equals 0 means 2, 4. It means 0, 4, and t equals 2 corresponds to 2, 0. Our orientation is in the wrong direction. So that's not going to work. That's not going to describe the line from 2, 0 to 0, 4. This parameterization for t between 0 and 2 goes from 0, 4 to 2, 0. So the reason that it's backwards is that the x's are going from 0 to 2, and we want the x's to go from 2 to 4. So one thing that we can do to adjust this is to change the orientation of the x. I'm going to make the x's go backwards. So I'm going to adjust the x. I'm just going to have to switch pages. We want to run the x's in the other direction. So let's see what we have to do. So we got this parameterization, which didn't work. X equals t, and y is equal to 4 minus 2t. This is the first thing we write if we have a function for our parameterization. And then we decided that we want t to run between 0 and 2. But this goes from 4, 0 to 2, 0. Oh, sorry, from 0, 4. Did it again. That's backwards. So let's flip the x's around and see what happens. So I'm going to replace x not with t. I want the x to go, instead of from 0 to 2, if I want the x's to go from 2 to 0, then I can just flip this around and say that x is 2 minus t. This will turn the x's around. Now when t is 2, x is 0. And when t is 2, x is 0. And when t is 0, x is 2. So that's how we switch the direction. Just take the endpoint and subtract the parameter, and that'll make the x's run the other direction. Now our y's, when we have y equals 4 minus 2t, that sends the y's from 4 down to 0. So in the 4 minus 2t, when t is equal to 0, y is 4. But when t is equal to 0, I want y to be 0, because I want to go from 2, 0 to 0, 4. So I want to flip the t's around, flip the y around as well. And since y is equal to 4 minus 2x, and x is now 2 minus t, I can just write y is equal to 4 minus 2 times x, which in this case is going to be 4 minus 2 times 2 minus t. Start with your function and replace with the parameterization, which we can simplify to 4 minus, let's see, minus 4, 0, and then plus 2t. Now when we plug in t equals 0, when t is equal to 0, then y is equal to 0. That's where we want the y's to start. And when t is equal to 2, y is equal to 4. Now we have the correct orientation. Any questions? This is why I didn't spend a lot of time practicing or writing parameterizations for curves, because now we're doing it in context. I knew later on we're going to have to parameterize some curves, so let's do that in service to some other problem so we can see where things are headed. So now we have the parameterization for C1. So R, let's call it R1 of t, is x is 2 minus t, I, plus y, which is 2t, times j. There's our parameterization of C1. Now let's remember what we're doing. We're integrating a line integral over this curve. So we're going to need little directional pieces of this curve. So I need r prime of t. So the derivative of 2 minus t is going to be minus 1. And the derivative of 2t is going to be 2. And all this is multiplied by the dt. So this is our dr. Now we can plug our x and our y into our x and y into our vector field, and our integral over C1 of f dot dr is going to be the integral. T goes from 0 to 2. Our f at xy is 6x I plus y times j. So our f is going to be 6 times x, which is 2 minus t, I, plus just y times j, 2t times j. This all here is the f at r. Then I have the dot product with dr dot minus I plus 2j dt. So here's f at r. Here's the dr. We go from 0 to 2. Any questions? This only seems like a lot to remember, because it's a lot to remember. There's a lot going on here, a lot of mechanical stuff. But it's getting in the way of kind of a simple idea. We're just evaluating the vector field at some point and finding the dot product of the direction the curve is headed. Here's the wind, and here's a little piece of the bird, not a piece of the bird, a piece of the bird's path flying in the wind. Now we want to think about, is the curve pushing into the vector field because the bird is flying into the wind, so we get negative values, or is the vector field pushing the bird, which means we're going to get positive values. So let's just continue our calculation. I'm going to clean this up a little bit. This is going to be 12 minus 6t. And I need to make a dot product. So we're going to be integrating from 0 to 2 this dot product. So 12 minus 6, I wrote I instead of t. Saved it. It's 12 minus 6t times negative 1. So I'll have 6t minus 12 plus 2t times the 2 dt. So this is the dot product. There's where we did the dot product. Now we need to integrate. So we got 6t and 4t is 10t. I don't want to write a whole thing. So now we'll integrate the function. We'll get 5t squared minus 12t. And then we'll evaluate from 0 to 2. So we'll have 5 times 2 squared minus 12 times 2 minus 5 times 0 squared minus 12 times 0. So we got 4 times 5 is 20 minus 24 is negative 4. Any questions? I just realized I don't have my headphones in, so I wasn't listening. If any of you had like a verbal question, I missed it. Any questions? Before we go on to the next curve, let's realize that the tricky part, the new thing that we had to learn here, was this process where we had to parameterize that curve. That's the tricky thing. But we start by parameterizing curves that we can describe as functions, so I can just make the independent variable the parameter and use that as a starting point. Just set up where x is the parameter, t, and then y is still the function of x, which becomes a function of t. Figure out what values of t you're going to have to use, what range you're going to use, and then just adjust the orientation. Make sure your orientation is correct. There's only 2 choices of which direction we're going to be headed along the curve. So if I said go from 0, 4 to 2, 0, then this is the parameterization that we want. But if I needed to turn it around to go from 2, 0 to 0, 4, then I just turn the x's around. T goes from 0 to 2, so x, if we write x as 2 minus t, then x will go from 2 down to 0. That's how to flip things around. So this parameterization goes from 2, 0 to 0, 4. That's the orientation that we want. That was the tricky thing in this problem, because that was the new thing in this problem. The rest of it was just taking some derivative to make the dr, which is a thing that we did before. Calculating a dot product, that's a thing that we did before. Finding an antiderivative, that's a thing that we did way before in the long, long ago. And then seeing that when we get this negative 4, making sure that this makes sense with our intuition about how the vector field and the curve play together. So if we go back to a picture of the curve and think about some values of the vector field. So if I calculate the vector field along, say at 0, 0, there's the vector field is 0, so that's not interesting. But if I go along the y-axis, I can see what the vector field is going to be doing. So the x's are all 0. And then let's see, the y is going to be just, let's see, 1. So there's going to be, when x is 1, there's going to be a vector going up. There's going to be a little bit longer vector going up. But then when I move over to, let's say, 1, 1, the vector is going to have a 6x and 1 in the y direction. So it's going to be at this 1/6 slope of 1/6. So that's definitely wind pushing against the bird trying to fly through the wind. If I go through to the point 2, 1, 2, that's going to be 6x, and then y is going to be 2. So it's going to be a little bit steeper. So we can see along the y-axis, the vector field is going to be pushing with the bird, but all the way up to that, the vector field is pushing away. So the vector field is pushing against the curve. So we should expect the line integral to come out negative. And that's what happened. Oops, that's not where it was. There it is. Any questions? Let's pause the video here. Let's pause the video here and talk about the next part of the problem. Oops. Now let's pause the video here.